All right, we got another new chapter here. This one's on momentum and its close cousin impulse, who we'll meet in just a little while. So first we need to start with what's called the conservation of momentum. So we had conservation of energy, right? What that meant was that energy could be changed forms and shift to different objects, but it could never be destroyed, right? Means exactly the same thing here. Momentum can change form, it can move to different objects, but momentum cannot disappear. Any interaction between two objects or three or four or however many objects, we're going to have the same amount of momentum in that system at the beginning as we are at the end, as long as it's what's called an isolated system, and we'll get to that in just a second. So what is momentum? Momentum is, we use a P, it's not momentum. Um, I don't know why we use a P. We run out of letters, basically. You know, we've got too many M's. So momentum is P, and it's defined like this: mass times velocity. And so the heavier an object is, or the faster it's moving, the more momentum it has, which matches our sort of everyday definition of momentum. And so momentum tries to quantify the tendency of mass to continue on its course. And so something heavy that is moving on a course it's going to be harder to change that direction, to stop that or speed it up, right? So it has more momentum. If it's moving faster, it's going to be a lot harder to bring that to a stop. So there are units, and we don't really have a clever name for them. You know, we could call it an Augsburger, I think. I think it'd be a great idea. Um, but it's just a kilogram meter per second, which also doesn't have a lot of intuitive sense. So we're not going to talk about the units much. So big picture is momentum is basically what you think it is. It's implies that a mass moving will require some force in order to change its direction or speed. And the heavier it is and the faster it's moving, the harder it is it's going to be to change that direction and speed. So that's momentum. Now we want to talk about what's called impulse. And impulse is a change in momentum, right? So we kind of go back to our definition and say mass moves unless a force changes its velocity, right? That's Newton's first law. And so Newton's first law is really tied together very closely with momentum. And so actually when Newton first wrote the second law, he wrote it with a P in it, with momentum. So here we have, here's our second law: sum of forces is equal to mass times acceleration. Now we'll do a little, math magic here. That acceleration is the same as velocity divided by time. We'll just rearrange some stuff. And here we have a term that if we bring that m inside the delta, then we have delta mv. In other words, the change in the product of mass and velocity. And that is the change in momentum. Okay, so we can say that the sum of forces is going to be equal to the change in momentum over the change in time. And then we can think about what that means. What this means is that a net force, that's what this guy is. Remember, the sum of forces is our net force, changes the momentum of an object based upon how long that force is applied, right? So we're gonna rearrange this equation one more time, and we're going to multiply both sides by delta t, right? And we're going to get delta p, the change in momentum, is that net force multiplied by how long that force is applied, right? So if I push something on a frictionless surface for a second, it's going to accelerate to a certain velocity, right? But if I push it for 2 seconds, it's going to have a higher velocity, okay? And that's going to mean it's going to have more momentum. So force times the time that the force is applied. And in this form, we call that change in momentum the impulse. Okay, so impulse and change and momentum are essentially the same thing. And so we have a nice three-part definition here that's going to help us solve a lot of problems. If we know the force and the time, we can find the impulse. If we know the initial momentum and the impulse, we can find the new momentum after that impulse has been applied to our object. All right. So before I mentioned the idea of conservation of momentum, and I said the conservation or the momentum of a system can't change. It can't be destroyed. Um, we have to think about that as within an isolated system. So what is an isolated system? It's a system in which no outside force is acting upon it. So we can think of that as really big, right? The Earth in short term is kind of an outside, is an isolated system, right? There's no pushing or pulling except gravitation with the sun. We'll ignore that for a second. So we can think of that system as really big, or it can be really small, like this rocket, right? So this rocket's going through the air. And if we ignore drag here, then the momentum of this system is going to be the same as the momentum of that system. Okay, so maybe there's a little explosion that separates your capsule from your booster rocket, right? But if we sum up the momentum of this guy and the momentum of that guy, it's going to be very similar to that one. A lot of times what we do is we just say, there aren't a lot of truly isolated systems. In fact, you could start looking at this and say, hey, Dr. Augsburger, what about gravity? That, don't worry about that. Let's imagine that this is a fraction of a second after that. And so a lot of isolated systems that we're going to talk about are not truly isolated. They just change so quickly that outside forces don't have a lot of time to change our momentum. Okay, so if we talk about, say, a collision, if we find the momentum right before the collision and the momentum right after the collision, we can say that that momentum is unchanged. Because sure, there was probably some drag force, there was probably some frictional forces there, but they had so little time to act that they're not going to make any significant change in our momentum. Okay, so momentum is conserved. That is, it's unchanged, the system, the momentum of the whole system in an isolated system. Okay. So go back to our rocket here. If we wanted to be more honest, we could say that in the x direction, in this direction, that gravity is acting only in the up-down direction. In this direction, it's an isolated system. Okay, so its x momentum in the left or right direction isn't going to change. In the up and down direction, it is going to change, right? It's going to have a lot of momentum going up, and then as gravity affects it, it's going to change that momentum. It's an outside force being applied here. That changes the momentum of the system. It has an impulse, right? Gravity is acting for a certain amount of time. And like I said before, if that time is really short, then we can say, oh, it's mostly isolated. And for our purposes, that does pretty well.